Hi and welcome everyone to this 11th video of BIOB20. In this video we're going to talk about linear regression. We start by creating a sample X to have something to work with. Let's say a random Gaussian sample with n equals 100. Then we create a variable y which has a linear relationship with x. So y is b times x. And here we're going to say that b is 2.3. And on top of this linear relationship, we're going to add some random noise, which is going to be Gaussian in this case. If I plot y versus x, I obtain a nice scatter plot with a linear relationship. But the relationship is not perfectly linear because of the random noise that was added to the variable y. The vertical dispersion is due to the Gaussian random noise. The task of linear regression is to go from this plot there to guess the value of 2.3 that was used to generate the linear relationship. Let's start with the trial and error approach first. We are creating a vector y underscore which has a perfect linear relationship with x. For example, y is 1 times x. I can now add the points x, y underscore in red to the existing graph. You can see that they lie on a straight line, but that this line is not so good. It does not really coincide with the impression that we have from the data. The vertical distances between the red points and the black points can be particularly large, especially on the extremes on the left and on the right. So I need to try something steeper. For instance, I could say y is 2 times x. I now add the points in blue to the existing graph. It is obvious that the blue slope is much better than the red slope. To make progress on this question and to find the optimum, we're going to focus on the vertical distances between the data and these perfect points that are in a linear relationship with x. So we will examine y underscore minus y. We have a whole series of vertical deviations and we'd like those to be as close to zero as possible. However, they cannot be zero because we have added the Gaussian random noise. So we know that achieving zero is strictly impossible. And because we're now modeling a Gaussian random process, we can use maximum likelihood estimation. So we use d norm on these vertical deviations, y underscore minus y, to give us the probability of observing each and every number. And we search the value of the slope for which they are all as plausible as possible. By taking the product, we obtain the overall likelihood for all the values together. The value we obtain here is for the slope 2. The values of likelihood are tiny, so we typically work with their logarithms. When we request the log of the probability, we have to replace the product by the sum. We then obtain the log likelihood. And of course, if we compute the log of the value we obtained previously, we now obtain the same log likelihood. Now that I have a way to compute the log likelihood automatically, I can test what happens for another value of the slope, like 2.1 for instance. The log likelihood is higher, so I should prefer 2.1 over 2. And to answer this question in full, we can use a for loop. I'm going to try the values of b between 1 and 3 by increment of 0.1. And I store this in the vector b's. I will also store the log likelihoods in the vector LLS, and I initialize it with NAs. We have 21 values in total, so I say for I in 1 to 21, and then in the body of the loop I create the value of y underscore, and for this I use the ith value of b, and I compute the ith log likelihood the same way as I computed it before. If I now inspect the values of the log likelihood, I can see that there is a conspicuous maximum. With the function whichMax, I can get the index of this maximum, and I see that this is at position 14. And when we look at the value of b at position 14, we can see that this is equal to 2.3. This is exactly the value that we had chosen initially. We can now plot again y versus x. And if we define y underscore as 2.3 times x, we can add these points to the graph and see that this is a fairly good fit. And this is not just fairly good, this is the optimum in the sense of the maximum likelihood estimation. The general case may be more complicated. Let's create another example with 100 random points. We're going to say that y is again 2.3 times x, but we're going to add a constant, say 4.5, and we're going to say that the Gaussian noise has a standard deviation of 1.9. We can still use the maximum likelihood method, but it becomes a little bit more complicated. When we plot y versus x, we see that nothing fundamental has changed. It's still a linear relationship between x and y with some random noise. In such cases, R can do the automatic maximum likelihood estimation for us. Here, the function of interest is LM for a linear model. The code is a little peculiar because we have to use the tilde notation to express the fact that y is a linear function of x. And this gives us the estimated coefficients. The intercept is the first here on the left, and the slope is the second there on the right. You can see that in this case, the maximum likelihood estimation of the slope is somewhat far away from the original. There is an easy way to add this line to the existing plot. For this, we just have to say AB line and plug in the output of the LM function above. And as usual, we can choose a different color, like red for instance. This is the regression line, where the slope and the intercept were estimated with the maximum likelihood estimation method. In a sense, this is the same method as we've seen in the first part, except that we have estimated 3 parameters at the same time. The standard deviation of the Gaussian was also estimated, but it's not showed in the output. So whenever you want to use a linear regression in R, the preferred way of doing it is to use the function LM. That's what I wanted to share with you. Good luck with the quiz, and see you at the lecture.